the organizers for the kind invitation. Really wonderful to be here. And my talk is going to be somewhat different from most talks we've heard this week. So there's not going to be a lot of topology in it. In fact, I probably can't discern any topology, but there are going to be some defects. To begin with, we've heard a lot about various kinds of topological defects in quantum field theories, where you can you can smoothly deform the defect, and that doesn't change any correlation functions as long as you don't cross other operator insertions. And there's been, of course, a tremendous progress in understanding such objects, their junctions, and so forth. But what about more general defects which are not topological? And here our understanding is much more limited, and in many cases we are just kind of understanding them example by example. So I'm going to give you a couple of examples where we've made some progress, and I'll be focusing actually on line defects. And line defects are very natural in quantum systems, because they really correspond to some kind of impurities, right? An impurity in space localized at a point in the space-time path integral maps to a line defect, and so there's a venerable history study of such objects. So I'm going to talk about two examples. The first is going to be the Kondo model at large impurity spin, and the second example, if I have time, will be about a fixed spin line defect in the 3D probability. So let me begin with the Kondo model. So this is work with my PhD student, Abhijit Krishnan at MIT. And I'd like to point out some related work by Hu and Si from 2 years ago, and I'll point out exactly where the similarities and differences are. Okay, so the Kondo model is one of kind of paradigmal problems in condensed matter physics. So it's about, you take a three-dimensional, or in fact any dimensional free fermion gas, and you immerse a spin impurity into it, and you study the behavior of this system as you lower the temperature. And actually, this is one of the oldest problems in quantum theory. I think, well, first of all, such objects actually exist. You can such magnetic spin impurities appear naturally in many materials, and they lead to signatures in experiments in resistivity and susceptibility and so forth. And actually, I think the first experiment to notice that such impurities have an effect was done like in 1930s. So this is a really old, venerable problem, and I'll tell you about some progress we've made on. And now,
sorry, what is the coupling between the path and the?
I'll explain in a second. So the coupling is just you take the electron spin, add the impurity, and couple it to the impurity spin. Just spin-spin interaction. I'll write down the action in a second. But nice thing about this problem is that even though you can formulate it in any dimension, as long as the coupling between the electrons and the impurity is spherically symmetric, you can just map it to because the electrons are free, you can just map it to a one-dimensional problem, 1 + 1 dimensional problem, where you have a semi-infinite system of free one-dimensional electrons, fermions, and you have the impurity spin at its boundary, and there is a coupling. And well, when the coupling is anti-ferromagnetic, what happens is that if you start with the weak coupling, your system flows away from the weak coupling, from the free spin fixed point, And was believed to happen, and I'll explain where this comes from. It's believed that in the infrared, you end up reducing the spin of this impurity by half, and you end up with effectively decoupled electrons with a phase shift of pi. So you can kind of think of, one of the electrons comes in and forms, tries to reduce the spin of this impurity by half, so lowers the spin. And well, what is the understanding? Well, we understand from a renormalization group perspective, we understand the flow away from the UV fixed point. We understand the flow towards the infrared fixed point. If you want to understand the entire crossover, then we have to rely on an exact solution, which is through beta ansatz. And it captures many properties such as thermodynamics, say the entropy of the impurity and so forth. But many quantities are difficult to extract, as we know from beta ansatz, such as correlation functions, so forth.
Sorry.
Yes.
About this reduction to the problem, I guess the procedure is that you take the wave function of the electron, you do a partial wave expansion.
Exactly.
Is this procedure of keeping only the S wave a rigorously justified procedure, or is just a lore that is work?
Well, depends on depends on the problem that you start with. But if your interaction of the electrons with the impurity is spherically symmetric, then it's rigorously justified.
There's also Anderson's model, which takes S wave and T wave into account.
Okay, so it's a better approximation.
Well, in real materials, of course, if you don't have full rotational symmetry, you have the lattice, so you have to, in principle, you might need to think about all of those issues. But here we will just work with this one dimensional.
But even if the problem is spherically symmetric, there might be phenomenon for which the angular momentum matters. So
I think the other modes just decouple, right? The other angular momentum models modes just don't couple to the impurity.
okay, so
Yes.
it's difficult.
Okay, so what we've been able to do is, if the impurity spin is large, we've been able to track the entire crossover from the UV fixed point to the IR fixed point with renormalization group. And the results, as I'll show, match with beta ansatz. So there is an interesting generalization of the model where you take the fermions to have K flavors. So there's SUK symmetry. And in this case, the physics depends on whether the flavor number is bigger than 2s or smaller than 2s. So if the flavor number is smaller than 2s, then the physics is very similar to the single channel case. So people call this number of flavors, they call it number of channels. Very similar to the single channel case, which is your in the infrared, your impurity as spin magnitude is just reduced by k over 2. And then you just have a kind of pi phase shift for the fermions. More interesting situation is when the number of channels is bigger than 2s. So this is known as the overscreened regime. This is known as the underscreened regime. Why it's underscreened? Well, you don't fully screen the impurity in the infrared. And here you end up with a non-trivial boundary fixed point described by SU2 level K boundary CFT. Right. And turns out that again, when the spin magnitude, when the impurity spin magnitude is large and the number of channels is large, but we keep the ratio between them fixed, we can understand the crossover between this UV fixed point and the infrared fixed point using renormalization group. The only case where we cannot understand the full crossover is for the fully screen case when number of channels is equal to 2s, then the renormalization group fails, breaks down in the final stages of the RG flow. And I should say that the renormalization group equations that we derive are actually the same as those in this paper by Hu and Si, even though our method is slightly different. But the important difference is that they only focused on this K, on this fully screened regime, and somehow failed to notice that you can access particularly this interesting overscreen.
What does it mean that the RG phase means that at some point you become strongly coupled and you don't know
That's
what
right.
to do?
That's right. Yeah. So what controls the expansion here is this parameter s, 1/s, and at some point the 1/s expansion breaks down effectively because your spin, the magnitude of your spin gets reduced, and when it's reduced, when in this kappa equal 2 case, in the infrared you're kind of left with just 0 spin and a pi phase shift for the electrons. So now because your spin is small, you no longer have a controlled expansion.
So what should I expect? That at some point there will be bound states and the low energy degrees of freedom are different from what you're describing?
Well, I'll explain our renormalization group procedure, so you'll see exactly how things arise.
And what do you mean by SU2 level K? Because I understand the system is two-dimensional. There is a one-dimensional boundary. What do you
Yes.
mean by SU2 level K?
Well, so it's SU2 level K CFT, right? So these K free fermions, you can embed, you can split it up as you have a U1 sector, you have the flavor sector, and you have the SU2 sector, the spin sector. And the interaction is only in the SU2 sector, and then in that SU2 level K, it's
So the whole two-dimensional CFT becomes a WSW model.
that's right, exactly.
What's the boundary condition for
Uh,
so you have a boundary, you have a 1+1 DCFT with a boundary condition.
that's right.
So you are picking one particular card D state of
It's a particular. That's right. Absolutely.
Okay.
Yeah. It's
Which one?
it turns out that essentially your impurity gets fully subsumed into this SU2 level K.
Sorry.
So you will end up having boundary boundary primaries with identity, then dimension 1, then j equal 1, j equal 2, up to j equal k over 2.
Okay.
So maybe I should have.
What's the natural of the phase transition complex would be? Like is it first order, second order?
Good. I don't know if you can think of it. You can only maybe think of it in this S to infinity, K to infinity.
Effectively, it's like a continuous.
Yeah.
Very similar to the large N QCD, large flavor QCD. Like imagine S is like the color number and K is like a flavor number, and there's a limit similar to the one you just described. And like for people, believe there's some complicated transition as you adjust the image. I'm just curious whether there's some.
Well, later when I show our results, you'll see that actually there will be some kind of branch cut in the energy. It's like this K over S will be like an angle around angle in the complex plane, and then the energy will be like the radial direction in the complex plane, and there is going to be a branch cut when K over S is equal to 2. So it's kind of some interesting analytic structure that I don't know if there is any significance. I should have said maybe that this multi-channel problem also, we understand the UV fixed point and the flow away from the UV fixed point from RG. This and we understand the infrared fixed point and the flow towards it from RG. But again, to understand the full crossover previously, you needed to rely on beta ansatz solution. But now in this double scaling limit, we can understand the entire crossover just using renormalization. So, why now? Why wasn't this done like 40 years ago or something? 30 years ago. In the last few years, there've been progress on a class of problems involving defects or boundaries, where on the defect, you have some degrees of freedom which are essentially semi-classical. The bulk is, in some sense, fully quantum. And the coupling of such semi-classical degrees of freedom on the boundary to the fully quantum bulk, in some cases, you have analytical control. So first example that was recently considered is this problem of boundary behavior in the three-dimensional ON-CFT, so the Wilson-Fisher conformal field theory. And here we found this new boundary universality class where the order parameter on the boundary, the correlation function decays very slowly. So the order parameter on the boundary is almost ordered. So that's an example of kind of almost classical boundary. And then the technology that we developed for this problem was generalized by Gabriel Coma and collaborators to the problem of spin impurities in the, again, three-dimensional O3 conformal field theory. So now these are line defects instead of two-dimensional defects or boundaries. And again, here the large spin expansion. So again, they could control this using in the limit when the impurity spin is large. And our approach to the quantum model will be similar to, in particular, to this methodology, although there will be some new elements, new interest. Okay, so that's the setup. Now let's get to the method. So again, we start with on the model in this reduced to this 1+1 dimensional boundary problem. So what do we have in the bulk? We just have C=1 free fermion theory with a just this boundary condition. And on the boundary, we start with a spin S, right? So there is a Berry phase or geometric phase term in the action for this spin S. And then there is this coupling between the fermions on the boundary and the spin, right? Someone asked about this coupling, so this is the coupling. Okay, so we'd like to understand this problem in the limit when the impurity spin is large. So when the impurity spin is large, it's almost classical, right? So it's almost like just a fixed vector. Let's begin by fixing the direction of this impurity spin as, let's say, it's points along the Z direction, right? So then this interaction term just becomes like a magnetic field on the boundary for the fermions, or like a boundary potential for the up and down fermions of opposite side. So this will lead to a phase shift for the up and down electrons, which is opposite. So phase shift rho. And when the coupling J is small, then this phase shift is small. Well, we want to study the problem in the regime when the coupling is small, but in principle, this kind of formula allows us to go to arbitrary value of the phase shift. And later we'll find that even if you start with a small phase shift, it flows under renormalization group to large values. So it's convenient to consider the entire line of these fixed points of the free fermion theory characterized by this phase shift rho. So in the limit when the impurity spin is infinite, that's all you have. You have the impurity, the spin is frozen along, say, third direction, and you have this free fermion theory with the phase shift rho. What are the boundary operators of this free fermion theory? By the way, I call this free fermion theory as frozen. Well, there are three types of operators. So there is this operator that just tunes you along this line of fixed points, just changes the phase shift rho. There are these bilinears that correspond to essentially tilting the direction of the magnetic field or of the spin on the boundary. And then there is this just fermion density on the boundary. This is odd under particle hole symmetry. So if you start with a particle hole symmetric regularization of your theory, you will not induce this term. Okay, so that's the limit when spin is strictly infinite. What happens when you have a finite value of the impurity spin? Well, then you'll have fluctuations of the impurity spin, and let's consider fluctuations around, let's say, the North Pole, right? So this pi1, pi2 characterize the fluctuations, and naturally these fluctuations will couple to the operators of the Rosen, of this free fermion theory with the phase shift rho. So this will be this interaction term here. As B of n, that's just the Berry phase term or the geometric phase term in the action for the spin, and I'll explain what these contact terms are in a second. Let's begin by fixing the interactions between the fluctuations of the spin and the fermion bilinears. And these interactions turn out to be completely fixed by the spin rotation symmetry. So we are using a description of the theory which is not manifestly spin rotation invariant. We are kind of expanding around this North Pole on the unit sphere, but rotational invariance needs to be restored. And now we are going to kind of restore it order by order in these fluctuations pi. Well, how does rotational invariance look, right? So under a global SO3 or SU2 spin rotation, the bulk fields transform in this way, and the spin also rotates. Now, when we fix the spin to point along the z direction and obtain this free fermion action here with the phase shift rho, clearly this action is not going to be invariant under rotations because you chose that particular axis. So it will transform under this global rotation. By how much will it transform? Well, we actually know, right? To implement a symmetry transformation on some region of space-time, you need to enclose that region with an integral of the current over the boundary, current normal to the boundary. So if you want to implement an spin rotation on the entire bulk, then we just pull this contour all the way to the boundary, and we end up with an integral of the current perpendicular to the boundary. In fact, these are the components of the current corresponding to the SO3 generators, which are broken by the direction of the spin that we chose.
Why are we sure that rotational invariance is not spontaneously broken?
That what's not?
Why are we sure that rotational invariance is not spontaneously broken?
It might be spontaneously broken at the end, but the action should be rotationally invariant. So we want to, the action should be rotationally invariant, and then whether the vacuum is rotationally invariant, that's a different question. Yeah. So right, so we see that this term transforms in this manner under a spin rotation transformation. So in the interaction term, there must be something that compensates this transformation, and that's exactly fixes the coupling of the fermion bilinears, boundary fermion bilinears from this action to the fluctuations pi to leading to first order in pi. And in principle, okay, so this is kind of a very elegant procedure. It kind of gives you a universal form of the coupling. Now, because at each value of the phase shift, we can relate the right-handed and left-handed fields at the boundary. So we can actually rewrite this current entirely in terms of the right movers. And this is instructive because you see that when the phase shift rho is equal to pi, then this current vanishes. Well, that's not too surprising because when the phase shift is equal to pi, right, this boundary condition is actually SO3 symmetric, rotationally symmetric. So this action here is already rotationally symmetric, so you don't need to restore the symmetry anymore. So we'll find that actually at rho equal to pi will turn out to be our infrared fixed point in this single channel case. And at that fixed point, we'll see that the fermions entirely decouple from the impurity or whatever is left of the impurity. Okay, so I fixed the first order term in the spin fluctuation here. One can fix higher order terms. I don't have as elegant an argument, but one can just do it by brute force. For instance, you know that if you do a rigid rotation of your impurity spin, that all the correlation functions in the bulk should also rigidly rotate. So you just require that the correlation functions in the bulk rigidly rotate when you expand, when you do perturbation theory. You can choose this fluctuation to be constant in time and just do perturbation theory. And this way you can obtain higher order couplings of pi to the operators of S frozen. And this is, for instance, the quadratic coupling, and we fix the coefficient. Okay, so this is the way to fix the interaction term here. And then last object to fix is the so-called contact terms. So first of all, there is some regularization assumed when you write an expression like this. And depending on what regularization you choose, when you integrate the fermions out, you might end up with some kind of contact term for the fluctuations pi. And you have to be careful about these contact terms. And again, they will be fixed by spin rotation symmetry. And actually, the way we leading order in the fluctuations, we fix them as follows. So remember, in the geometric phase, if you expand the geometric phase in spin fluctuations, you'll have a term like this, where the coefficient will be just the impurity magnitude S. And then there are terms which are higher order in pi. And turns out that we need a contact term in this action of the same form. And to fix the coefficient of this contact term, what you can do is you can consider, instead of a semi-infinite line, you can think about a finite segment of your free fermion wire, and the total spin on this finite segment must be quantized. Now, because this segment is finite, you can integrate the fermions out. They'll be gapped. They'll have a 1/L gap, where L is the length of the segment. And you'll see that induces an effective Berry phase term, correction to the Berry phase term of this form. So you'll need a contact term to cancel it out. So this way we can fix the coefficient of the contact term, and this is the form in terms of the. And there is something interesting here, which is that when the phase shift is equal to pi, this contact term gives you a correction to the spin, which is -1/2. So we'll see that actually, as the phase shift changes from 0 to pi, the impurity spin gets reduced by 1/2. So that's exactly our ultraviolet fixed point, where the spin went from impurity spin went from S to S -1/2. You can also similarly fix contact terms in how an external magnetic field couples to your action. I'll skip this part. Okay, but so now we've fixed all the terms in the effective action for the spin fluctuations and their coupling to the operators of this free fermion theory. And now, well, we have single free parameter in the theory, which is this phase shift rho. So we can study how this phase shift rho flows under a normalization group. And what controls the calculation is that, the spin fluctuations are suppressed by this parameter s, right? So there will be 1 over s in the denominator of pi. So we do standard normalization group, you look, say, at this coupling, it will have current correlation. At second order, it will induce a current correlation function. In the OP of two currents, you'll have the third current. So, and this will exactly lead to a flow of your phase shift rho, because remember, this is exactly an operator that tunes you along the line of fixed points. So you end up with this equation for the beta function of the phase shift rho. So this is exact beta function. It's not perturbative on the phase shift, but what controls it is this parameter 1 over s. And then there are higher order corrections as well. When the phase shift is small, this agrees with the perturbative beta function, which is well known from old literature. But the nice thing is that you're not limited to weak coupling. You can go to arbitrary phase shift rho, and what you find is that rho flows from 0 to pi. And as we said, when rho is equal to pi, the effective impurity spin is reduced by 1/2. So that's exactly the underscreened fixed point where the impurity spin gets reduced.
This one loop, this beta function is a one loop effect, or is classically computed? How?
Well, right, so it's an expansion in 1 over s, right? And what you're utilizing is that when s equal infinity, you have this line of fixed points characterized by the phase shift, and you don't need to work at small phase shift, you can work at arbitrarily large phase shift. So it is one loop in the sense that, in the pi fluctuations, you just go to one loop. But the preliminary work that you've done was to understand the theory with the phase shift rho at any rho. So you start with this line of fixed points, and now you kind of move very slowly along this line. And then, you can compute physical quantities such as the impurity entropy, the impurity susceptibility, the impurity magnetization. And again, you do this in the 1 over s expansion, and you RG improve your results using this RG flow. Okay. So, and the results agree with the exact beta ansatz solution to this order in 1 over. So we understood the full crossover now between the UV and infrared. Okay, what about the generalization to the multi-channel case? So here the physics is even more rich. Okay, so how is the problem defined? Well, you just extend your bulk fermions to have k flavors. So this W is now the flavor index, and the flavors are all coupled with the same coupling to the impurity spin. And now we turn the same crank, right? So in the limit when the impurity spin is large, it can be first taken to be fixed, let's say along the third direction. There is a phase shift for up electrons and an opposite phase shift for the down electrons. And we turn the same crank, we get this effective action. The only difference from the single channel case is that now in the contact terms, there will be a coefficient k here, because each flavor will contribute to the contact term. Okay. Now, like I said, this action can be analyzed in the limit when k and s are large, but the ratio is fixed. The reason is, if you think about integrating the fermions out, right? So this just coupled quadratically to the fermions, you'll get some effective action for the fluctuations with a coefficient k in front. And when k is large, you can use saddle point technique, right? So just standard kind of saddle point calculation. And then turning the crank, you can get the beta function for the phase shift rho. And now this beta function looks a little bit more interesting than it did in the single channel case. So there is some non-trivial algebraic function here. I should say that this beta function agrees after a change of variables with the results of Hu and C. But what we point out is that actually when the number of channels is bigger than 2s, there is this interesting overscreened fixed point at phase shift smaller than pi that is accessible here, and your phase shift will flow to this fixed point. In the underscreen case, the physics is similar to the single channel case in that you flow to rho equal pi.
If you push it in the negative rho direction, then it becomes non-perturbative, the flow.
In the negative
Negative rho
from
the opposite direction from zero.
yeah.
So here you you're pushing it in the positive direction, and you zero, the zero you see the positive value. If you start out in the negative direction, then you don't see that.
Yeah, so then if you start with small negative rho, right, it's ferromagnetic condor, right? So you flow towards zero.
Flow
You flow
back.
back to zero. Yeah. So that's why the antiferromagnetic case, that's the where when you have the interesting crossover.
I mean, it's a kind of well established. Nobody thinks there is some, at higher orders, there will be some zero in the,
Ferromagnetic. You're asking ferromagnetic condor whether there is something interesting
yeah.
at large.
I mean, perturbatively, yes, it should, it wants. to go back, so it's sort of
The problem is that
irrelevant perturbation, but at larger values of the coupling.
the problem, I think, will be that you have to be careful about defining the problem non-perturbatively then, right? Because here you're lucky, you have kind of asymptotic freedom, right? So your theory is kind of well defined. You can start from weak coupling and then you flow to some strong coupling fixed point. If you need to go to strong coupling from the very beginning to have something non-trivial, then there is issue about how is the it's kind of not field theory, not defined within field theory. Okay. So let's focus on this overscreen case. And nice thing is actually that this beta function, even though it looks kind of complicated, can be integrated. And this is the expression for the phase shift as a function of energy scale. And what appears here is this Lambert W function, also known as product log function. And this goes back to a question that was asked by, I think, Shen, that this channel number, or this number kappa, looks like a angular direction in the complex plane here, and then this omega, right, is the energy scale. So the energy scale looks like the radial direction, and there is some branch cut in this function when the phase is equal to pi, when kappa is equal to 2. Anyway, so that's some interesting analytic structure here. But from this expression, you can extract all sorts of physical quantities, like you can extract the correction to scaling exponent at the infrared fixed point, and to leading order in K, it agrees with the exact result from the SU2 level K CFT. You can calculate the impurity entropy again as at the infrared fixed point. This agrees with the exact impurity entropy from SU2 level K. Yeah, you can compute the impurity susceptibility, and all of these quantities agree with also the exact beta ansatz solution in the limit of large spin and large channel number. Actually, the interesting, so this like I said, this some very non-trivial function here, and the existence of this large spin, large channel number limit was gleaned from beta ansatz solution by Cvelik and Wigman, but they didn't have any kind of analytic way to understand it using randomization group, whereas now we do. Okay, so this is all I'm going to tell you about the classic Conda problem. I focused on observables that can be matched with beta ansatz, like the impurity entropy. But in principle, in our approach, we can also calculate various spectral functions and resistivity, which is something that beta ansatz cannot really do. I think, we work to leading non-trivial order in 1/s. One can consider 1/s corrections. I think that's just technical issue. But more qualitatively, I think some of the same ideas might be useful to study problems involving multiple Kondo impurities and arrays of Kondo impurities like this, where it's been argued that if you have an array of Kondo impurities, one-dimensional array embedded in a 2D or 3D metal, then you can actually have long-range order along the array. And I think this renormalization group technology that we developed might be useful for tackling this problem more rigorously. How am I doing on time?
Oh, fine.
Oh, I do fine. Very good. Okay, so
Can I ask you, so from the previous question, sorry, previous slide, so what goes wrong exactly, kappa equal to 2? Because, I mean, I understand there is a branch cut, but you might say, okay, let's just go through the branch cut on the correct sheet. And,
yeah, so we understand both kappa greater than 2 and kappa smaller than 2. The issue is exactly with kappa equal to 2. And what you actually find, well, so
is there some something divergent?
there is a divergence, which is that if you look at the effective propagator of this pi, right, there is there's a factor of s out front, or k out front here in the action, but when kappa is equal to 2, when you look at the effective action for pi, the coefficient in front will become small, right? So because s will be reduced by k over 2 effectively, and it becomes small, and then your perturbative expansion breaks down. And actually, in the RG flow, if you just integrate this beta function, as we did, if you set kappa equal to 2, you actually hit rho equal pi in a finite RG time. So that's kind of unphysical behavior. You cannot go to lower energy. It's just yeah, but that's a reflection of the fact that your 1/s expansion breaks down. Okay, so in the last I guess 10 or so minutes, let me talk about another impurity problem we've been thinking about with Ryan Lanzetta and Sheng Liu. I should say Ryan is a graduate student at University of Washington, Seattle, who is moving as a postdoc to Perimeter Institute, and he has been really the main driver of this project. Sheng Liu is a postdoc at KATP. Okay, so like I said, the problem of impurities in a quantum system generally maps to that of line defects in space-time. And we already talked about the famous example of the Kondo model, but now we'd like to consider more general impurities and more general bulk states. And let's maybe begin with bulk states described by conformal field theory. And we'd like now to go beyond 1 + 1 dimension. And once you go beyond 1 + 1 dimension, actually very little is known. So one actually question that I was curious about is whether you can have long-range order on the line defect. Someone asked about breaking of the symmetry, spontaneous breaking of the symmetry. So let's think about a discrete symmetry, right? So we know that if you have a purely one-dimensional classical system with short-range interactions, then at finite temperature, it cannot have long-range order, right? You always have a finite correlation length. On the other hand, if you have a one-dimensional classical system with interactions that follow off as power law, with sufficiently small power law, then you can have long-range order. Now, if you have a local system and you have a line defect in that local system, and suppose the bulk is described by a conformal field theory, right? So the bulk is critical. Can the critical bulk fluctuations effectively induce power law interactions on the defect such that you have long range order? So that's the question that I wanted to understand. And very concretely, you might ask, suppose you have a three-dimensional Ising model, the simplest StatMech model we know, right? So you just have spins sigma for plus minus 1 living on sides of a cubic lattice, and these are coupled with some ferromagnetic interaction. And suppose you tune the interaction on the defect, on the line defect, to be much bigger than in the bulk, right? Such that the spins on the defect kind of want to preferentially order. Now you tune the system, the temperature to the bulk critical temperature, right? Such that the bulk is critical. What happens along the defect? Can you have long range order on the defect? And well, there is a quantum interpretation of this that I'll skip. Just work in the classical picture, classical three-dimensional picture. So let's to answer this question. Let's first review why strictly in one dimension you cannot have, with local interactions, you cannot have long range order. It has to do with these domain wall configurations, right? Domain walls in one dimension cost you a finite energy, and then at finite temperature, the entropy associated with these domain walls will win over their energy cost, such that the domain walls always proliferate. So now, what's an analog of these considerations when we have a line defect embedded in a 3D critical system? Well, we can begin with a perfectly ordered state on the line defect. Say we fix all the spins to be plus on the line defect, and then we imagine flipping spins on some region such that you have two domain walls. And you ask about the difference in the partition function of free energy between the configuration with all plus and this configuration with two domain walls. And you expect from general scaling considerations this ratio to go as a power law in the defect, in the length of this minus interval. And this power delta domain wall, you can think of it as a scaling dimension of this domain wall operator, or defect changing operator. And if this scaling dimension is greater than 1, you expect the domain walls to be an irrelevant perturbation at this fixed spin line defect fixed point. It's kind of a no pun intended. Right, so then long range order on the line defect will be stable. Domain walls will not proliferate. So now, for any given bulk conformal field theory, you can ask this question. Start with a fixed spin line defect and calculate the domain wall scaling dimension and ask whether it's greater than 1 or smaller than 1. And in particular, you can start with a 3D classical Ising model, and you can ask this question.
So sorry, so these defects are conformal? Do they preserve conformal symmetry?
That's right. So if you start with, we believe that for the 3D Ising model, there is a conformal line defect, which can be obtained by integrating the sigma field, the order parameter, along a line, which flows to a conformal defect fixed point. Now, we will attack this problem using a new method of defect conformal bootstrap. And we will show that under reasonable assumptions, actually this scaling dimension is smaller than 1, so that for 3D Ising model, there is no longer, it's not possible to have a stable long range order on the defect. So, right. So in general, it's actually very hard to bootstrap defects. So we'll develop actually a new method that we expect to be much more general than this particular application. So you might know about conformal bootstrap for bulk CFTs, right? So you have some local operators, then you have operator product expansion, and you apply this operator product expansion to a 4-point function, and you get so-called crossing relations. you have these two channels that you can fuse the operators in. And then if a theory is unitary, you can apply powerful techniques of semi-definite programming to place constraints on the scaling dimensions and OP coefficients entering this crossing. So, there's famous success of this method is for the bulk of the 3D easing conformal field theory, we know scaling dimensions of low-lying operators to incredible precision, like 5 or 6 decimal. So how to apply same ideas to defects, in particular to line defects? Well, turns out that if you just consider an infinite defect, things don't work so well. In particular, you can think, say, about a 2-point function in the bulk, and you can think about fusion in the defect channel and in the bulk channel, but that gives rise to a system of crossing equation where you don't have positivity, so you cannot use this semi-definite programming techniques. So instead, what we found works is it works instead of infinite line defect to think about breaking up the line defect into 2 segments like this. And you can even consider a case where you have different line defect types living on this segment. Why is this configuration useful? So we want to think about the partition function of the system in the presence of these 2 line defect segments. Why is this configuration useful? Well, because you can think about fusing the endpoints of these defects in 2 ways. You can either think about fusing them to a point like this, and that gives you bulk operator. If you know something about the bulk spectrum of your theory, you can fit that into your bootstrap program. Conversely, you can also think about fusing the defect endpoints like this, and then that will give you an operator localized on the defect. So if A and B defect types are the same, that just gives you a local operator on the defect. If A and B are different defect types, that gives you an operator that kind of interpolates between the 2 defect types. So for instance, in the easing model, if A and B are defects with spins fixed as either up or down, then then operators that you'll get by fusion here will be the domain wall operator. They can access the domain wall operator.
Sorry, there is I think a third thing that you can do that is fuse the defect parallelly and then thinking like that.
How are you thinking?
So I take A and B, I fuse them parallelly.
Parallel means,
No,
oh, you want to think about them like this.
and then I link it.
So good. So here we will always think of the segments as being collinear. And we will use actually 1-dimensional conformal symmetry along that line. So it will end up being just 1-dimensional bootstrap. Yeah, it's interesting, if you can start moving them around, consider the non-collinear configuration, but we don't really know how to do that yet. Okay, so then, utilizing the system of crossing and putting in the information about the bulk spectrum of the, yes?
Is it obvious that you can cut the line?
So that's a very good question. So for general line defects, you might not be able to cut the defect. So this method only works for so-called endable line defects where you can really terminate. Very good. So this is, the application to the 3D easing model. So this is a kind of typical plot that you get when you're doing bootstrap. You have some region of parameter space that's allowed by the crossing equations. And here, what appears on the horizontal axis is the scaling dimension of this defect endpoint operator. And what appears on the vertical axis is kind of the defect central charge. So this would be, in a topological theory, this would be the quantum dimension of the defect. And then you see that, okay, so different colors correspond to kind of higher and higher numerical precision, or keeping more and more constraints in your crossing equation. And you see that as you keep more constraints, you end up separating out an island here in parameter space. And so it's a bootstrapper's dream. When you were able to isolate an island, you are super happy. So we believe that the physical defect actually sits physical defect in the 3D Ising model lives in this island. And then, you can look at this constraint on the dimension of the domain wall operator, again plotted against the same defect endpoint dimension. And again, you have some allowed region here. And if you compare the previous plot, the size of the island over the size of this island, the domain wall scaling dimension has to be smaller than 1. So you learn from this that the domain wall is a relevant perturbation to the fixed spin defect, and you cannot have stable spontaneous symmetry break. And it looks like you have actually, as you increase the strength of your, if you keep more and more constraints, it looks like this bounds saturate somewhere on the boundary of this exclusion region. And if you look at that point where they saturate, the values of the scaling dimensions are very close to what Yin-Chen He and his collaborators obtained by numerical method of exact diagonalization on the fuzzy sphere. So things seem to agree very well. Here's another such exclusion plot. Here, instead of the domain wall scaling dimension on the vertical axis, we have the subleading endpoint operator. And you see there is very sharp feature here. And if you look at this feature, again, you can extract the scaling dimension. Again, they agree very well with this fuzzy sphere exact diagonalization. Okay, so I'm almost done. Let me conclude by saying that we've developed here this new method to bootstrap line defects, endable line defects, and we hope that this method can be applied to more general conformal field theories, and in particular to study Wilson line defects in gauge theories, and maybe. Here we were feeding in information about the bulk to learn something about the defect, but maybe the existence of certain line defects can also teach you something about the bulk spectrum. So at this point, let me conclude and thank you.